Chapter 6. The Metrics and Methods of Measuring Soundscapes. Biophonies, bears, buzzers, breezes, birdies, and babbling brooks. Key terms to know before you read. Spectrogram. Visual representation of sound over time, frequency, amplitude. Baseline data. Initial recordings used for future comparison. Acoustic monitoring system. Equipment that records environmental sound continuously. GPS tracking. Location-based data collection tied to participant movement. Ecological validity. Real-world applicability of research findings. Low-impact research design. Methods that minimize environmental disturbance. Questions to consider while reading. How do researchers measure sound in remote environments without disturbing them? What does a spectrogram reveal that listening alone cannot? How can researchers connect exact sound exposure to human experience? Why is baseline data critical for long-term environmental monitoring? What practical challenges make field research character building? Advanced field methods in soundscape research. At some point, soundscape research stopped being an academic exercise and became something closer to an endurance sport with occasional wildlife supervision. Consider the field work conducted in places like Glacier National Park, where researchers hike miles into the backcountry carrying equipment that is heavy, fragile, and apparently irresistible to bears. This is not metaphorical. There are actual bears. Fieldwork now with added teeth. A typical research day in Glacier might include hiking 5.5 miles into the wilderness, gaining several thousand feet of elevation carrying equipment heavier than seems strictly necessary for listening. And then, just to keep things interesting, grizzly bears. Grizzlies, it turns out, are curious creatures. Unfortunately, their curiosity often expresses itself as what happens if I hit this expensive microphone. To address this, researchers deploy bear-resistant setups, electric bear fences. Yes, the same experiment that measures the subtle emotional effects of sound also includes mild electrification as a defensive strategy. Science contains multitudes. The art of being there without being there. Despite the chaos implied by hiking, cables, and wildlife deterrence, researchers follow strict low-impact protocols. Coordinate with park rangers, avoid sensitive ecosystems, and archaeological sites stabilize equipment using rocks or sandbags rather than permanent fixtures. The goal is simple. Collect excellent data while leaving the environment exactly as you found it, minus any bear-related incidents. Turning sound into something you can see. Listening is useful. Seeing sound, however, is where things get interesting. Enter the spectrogram. What it shows. A spectrogram displays time, left to right, often over hours or an entire day, frequency, low to high pitch, amplitude, loudness, shown as intensity or brightness. To the untrained eye, it resembles modern art. To a researcher, it is a detailed diary of everything that made noise. How to read it. Different sounds leave distinct visual fingerprints. Helicopters, thick, uneven bands, propeller planes repeating, patterned signals, high-altitude jets, small, diffuse puffs. The key idea is delightfully strange. You can identify sounds by looking at them. Following people around for science. Understanding sound is only half the story. The other half is understanding how people experience it. To do this, researchers employ a method that is both precise and slightly invasive in a polite, scientific way. The process. Hikers are approached and recruited on trails, often in places like Zion National Park. A GPS unit is attached to their backpack. Their movement is tracked throughout the hike. Acoustic monitors record sound exposure across the same landscape. After the hike, participants complete a survey measuring perceived sound quality, annoyance, overall experience. Why this is so effective? This method allows researchers to match exact sound exposure at a specific location with the participants' reported experience at that moment. In other words, it connects the physics of sound directly to human perception with impressive precision. Front-country convenience versus backcountry commitment. Not all research requires heroic hiking. Front-country, for example, Taylor Creek in Zion. Easy access on-site survey stations, higher visitor volume. Backcountry. Remote locations, lower human impact, more pristine soundscapes. Both are important. One offers convenience. The other offers authenticity and sore legs. What the data says, spoiler, people like quiet. After all this effort, what do researchers consistently find? People strongly value quiet environments. Natural sounds are highly preferred central to positive experiences. This may not be shocking, but it is now backed by extensive, carefully collected data involving GPS units, spectrograms, and at least one bear deterrent system. The big question: how much noise is too much? This is where research meets policy. Scientists aim to determine the threshold at which noise degrades experience. How this threshold varies by location, how parks can manage soundscapes effectively. Because while silence may be golden, it is also surprisingly difficult to regulate. Building a record for the future. In places like Grand Staircase Escalante National Monument, researchers are now focused on baseline data collection. What this looks like: 16 monitoring locations, about 2 months of recording per site, totaling 32 months of acoustic data. No visitor surveys, just sound. Why baseline data matters. This connects directly to the work of Bernie Krause. The idea is straightforward. Record environments, now compare them in the future. This allows researchers to track environmental change, monitor human impact, build long-term acoustic archives. It is essentially creating a time capsule, except instead of letters, it contains wind, birds, and the occasional distant aircraft. The equipment, surprisingly sophisticated, hopefully bear-proof. A typical monitoring site includes a microphone mounted on a tripod, a weather station measuring wind speed, temperature, humidity, underground cables, a protective case, often a rugged box housing, recorder batteries. The system is designed to be hidden, weather-resistant, durable. Ideally, it is also uninteresting to wildlife. Summary: advanced field methods integrate acoustics, psychology, and GPS tracking. Researchers use spectrograms to visualize and analyze sound patterns. GPS tracking links exact sound exposure to individual experience. Fieldwork presents challenges, including terrain, logistics, and wildlife. Baseline data collection supports long-term environmental monitoring. Studies consistently show that natural soundscapes are highly valued. Findings inform policy and park management decisions. Conclusion: modern soundscape research is a blend of precision science and controlled chaos. It involves high-tech equipment, detailed data analysis, and the occasional need to outwit a large, curious mammal. Yet the goal remains simple: to understand how sound shapes our experience of the world. And after miles of hiking, months of recording, and countless hours of analysis, the conclusion is both obvious and deeply satisfying. People prefer places where the loudest thing is nature itself. Chapter 8. Extreme quiet and the inescapable reach of human noise. There is a particular kind of silence people imagine when they set off into the desert. It usually involves wind whispering poetically through sandstone, perhaps a distant bird making a tasteful cameo, and absolutely no reminder that humanity invented both jet engines and tourism packages. As it turns out, reality is quieter in some places than you might expect and noisier in ways that are harder to escape. Key terms to know: noise floor. The lowest level of sound a recording device can detect. Soundscape. The total acoustic environment, including natural and human sound. Spectrogram. Visual representation of sound over time, frequency, and amplitude. Anthropogenic noise. Human-caused sound, often from distant sources like aircraft. Acoustic monitoring. Continuous recording of environmental sound using instruments. Questions to think about while reading. What does it mean for an environment to be quieter than measurable? Why might aircraft noise dominate even in remote natural areas? How do researchers distinguish between different sound sources? Why is the concept of a noise floor important for interpreting data? Can a place be both popular and extremely quiet at the same time? Into the slot canyons. The research takes place in Utah's slot canyons, specifically areas along hole-in-the-rock roads such as Peekaboo Gulch and Spooky Gulch. These locations manage an impressive balancing act. They are well known enough to appear on hiking lists, yet under the right conditions they can feel acoustically vacant, as though sound itself has taken the day off. Getting there, however, is less poetic. Field teams haul heavy equipment across uneven terrain, often in groups large enough to distribute the load without collapsing into a pile of exhausted graduate students. The work involves hiking, installing monitoring stations, and ensuring everything functions correctly. It is not a gentle stroll with a clipboard. The discovery of extreme quiet. In the Dry Fork Canyon system, researchers encountered something unexpected. The environment was so quiet that their instruments struggled to register it. Initial equipment could measure down to about 8 to 9 decibels. The canyon sound levels dropped to that threshold in practical terms. The place was quieter than the equipment could confirm. With more sensitive microphones, they later recorded levels around 5.7 decibels. That places these canyons among the quietest measured environments in the contiguous United States. This leads to an important realization. Silence is not simply the absence of people. It is also a function of timing, weather, and environmental conditions. A popular trail in winter can be quieter than a remote one in peak season. Equipment and measurement. The research setup is methodical and durable. Microphones capture ambient sound level meters record decibel levels, lithium-ion batteries power the system for nearly a month, weather stations track conditions like wind and temperature. Everything is stored in protective cases and carefully hidden. This serves two purposes: preserving the natural environment and preventing curious hikers or animals from turning expensive instruments into abstract art. Seeing sound, spectrograms. Once collected, sound data is visualized using spectrograms. These display time across a 24-hour period, frequency, indicating pitch, amplitude, representing loudness. Different sound sources leave distinct signatures. High-altitude jets appear as small, faint bursts. Other sounds occupy their own frequency bands. Even if the image looks like modern art, it contains a detailed acoustic fingerprint of the environment. The unexpected culprit. Aircraft noise. Here is where expectations quietly unravel. At locations like Calf Creek Trail, human-caused noise is audible about 70% of the time during peak periods. Most of that noise does not come from nearby visitors. The dominant source is distant aircraft, especially high-altitude jets. This is a critical point. The primary intrusion into natural soundscapes often comes from far above, not from the people sharing the trail with you. Core insight. Remote does not mean isolated from human influence. Aircraft noise travels long distances and infiltrates even protected environments. The idea that distance guarantees silence turns out to be optimistic. Why this matters? Natural quiet is more connection to research methods. This study demonstrates several key methodological tools. Acoustic monitoring for objective sound measurement, spectrogram analysis for identifying sound sources, noise, floor awareness to understand equipment limits, source comparison to distinguish aircraft from local noise. Likely exam questions. What is the noise floor, and why is it important? Where are some of the quietest environments in the United States? What is the primary source of human-caused noise in natural parks? How do spectrograms help identify different sounds? Why does aircraft noise remain significant in remote areas? Summary and conclusion. In the quietest corners of the American landscape, researchers discovered something both remarkable and mildly inconvenient. Silence can reach levels so low that instruments struggle to measure it, yet even these places are not immune to the distant hum of human activity. Slot canyons like Peekaboo and Spooky Gulch demonstrate that extreme quiet is real, measurable, and dependent on timing and conditions. At the same time, studies reveal that most human-caused noise in these environments originates not from hikers, but from aircraft passing far overhead. The result is a more nuanced understanding of soundscapes. Quiet is not guaranteed by remoteness, and noise is not confined to cities. Instead, both are shaped by a complex interaction of geography, technology, and human behavior. Or, put more simply, you can hike miles into the wilderness, find a place quieter than a whisper, and still be reminded that somewhere above you, someone is getting complimentary peanuts. Silence alone is worthy to be heard. Henry David Thoreau.